Good morning. Today we're live coding, and we're live coding on Studio development tools for diagnosing RaptorJIT virtual machine execution. And specifically, we're going to apply the Studio tools to resolve a genuine mystery. So we have a standard benchmark suite that runs for RaptorJIT, usually just as a kind of a sanity check to see if anything surprising has happened. It's kind of like a set of unit tests, you might say. And one of the benchmarks, every time we use it as an example, looks a bit funny. There's one benchmark that keeps running in interpreter mode when I think it should be running in JIT mode. So I thought I would now that we have the tooling up and running, we could use it to try to see if we can try and figure out what's going on with that benchmark. Why does it run in the interpreter? Why does it not run in the JIT? It would be pretty cool to see what we can work out there. And it's probable that along the way we'll find a couple of things, bits of information that are not quite at our fingertips, and we can just update the Smalltalk code in the UI to make that more accessible as we go. So let's hop in. I have made a to-do list, as I often do, so that we don't get lost. I'm going to check for check a suspicious benchmark, see what's going on. We might kind of in parallel with that make some extensions to the user interface as we need, if we need to. And there are a couple of things that have just happened again and again in these live coding sessions. One is that if we run a fragment of Lua code, it gets a really ugly generated file name that makes the debug printouts a little bit ugly. And the other is that anytime we get an error in a Nix build, like a syntax error in some Lua code that we've entered, we don't get decent error reportage. So those are both things that if they cross our paths, we might actually stop and fix them this time rather than putting them to the side and carrying on. But for now, let's go in. We have a brand new, fresh Studio inspector where we can enter a Nix expression to specify something that we want to build and diagnose. And I'm going to say that we want to use RaptorJIT to run a tarball of Lua source code at a URL on my repository. With that URL, it's just a repository on GitHub we're going to check out, and we're going to run every Lua source file that appears at the top level of that tarball, and then we're going to get a profiler report, and we're going to have a look around there. And it's going to be something that warrants a bit of thought and inspection. So it's running now, it's downloading that tarball and running the benchmarks. Now we have the results. So it ran 5 different benchmarks, well 6 if we scroll apparently, and the thing that jumps out is this very first one here. It spends very little time running machine code. It spends almost all of its time in the virtual machine, and that's not necessarily a bad thing. It just surprises me a little bit, and so I think it's worth actually looking at. I've seen this so many times. Most of them are running 99.9 say percent or 99% time in generated JITted machine code, but this one runs mostly in the virtual machine. There may be an innocent explanation for that. But there might also not be an innocent explanation. That might be because of a genuine problem, maybe even something that I've changed that worked in LuaJIT that doesn't work in RaptorJIT. So what we're going to do now is just dig in. So if we click on this, then it's going to go off and chug along, and it's going to show us all of the source code locations where code got jittered and how many profiler samples there were. So there's a lot. I mean, there's just a lot. Normally, it's just a lot of different bits of source code that have been jittered. So I don't immediately know the reason. So this solver, why don't we actually open up the source file as a first step and see what's going on, because we can see that a lot of code has been generated, and a lot of the profiler samples have been kind of widely distributed. Maybe if we take a look in there, we pick this first one, had the most samples. It has a trace that goes into the interpreter, which is the hottest. There's generally a lot of code that is entering the interpreter, and maybe the other ones follow a similar pattern. Yes. So what we're seeing is a lot of the JIT has very often generated code that bails out of machine code land and goes into the interpreter, and from a lot of different places. Like, this is not something that's happening once. It looks like something that's happening maybe 100 times or something in total. So this is something to have a look at. So let's find this solver code and see what the story is. Oh, and well, I guess before we do that, we can use the new feature that we added, where you can select a trace and you can come up to this JIT tab and say, well, what were the JIT events related to this this compilation? And we had a bit of a browse in here yesterday and saw some interesting things. We give that a moment to run. It's a little bit sluggish today. Yeah, so here we see a bunch of aborts and finally a successful zero bytecode trace, which is just a bit of glue to get into the interpreter. So we had an abort, and the reason was, yeah, loop unroll limit reached. I've seen that before just in passing. Another abort, loop unroll limit reached, and so on. So it seems like somehow this code, I mean, in this case, it had recorded a kind of linear stretch of code that had executed more than 2,000 bytecodes, which is a lot. It's a lot of code, and then it errored out to say that it had unrolled a loop more than it was comfortable with in the JIT, and so presumably there's a loop somewhere in the source code, and the JIT is trying to unroll this into a fixed length, a fixed number of iterations, but it's crossing a threshold where it just can't unroll that much. It doesn't think it's a good idea to unroll that much, and it's giving up and using the interpreter instead. So now let's look into the source code and see if we can see any obvious reason why it would be unrolling loops too much. So I have the source here. It was Meteor, right? Hop over and check. Oops, that's a VM profile file. Solver was the name of the source file. What was the name of the profile set? Yes, Meteor. Okay. Shouldn't have opened the profiler data in Emacs. I want to get the source code. Here we go. Meteor. What does this benchmark do? Generate a decision tree based solver for the Meteor puzzle. So I'm just thinking aloud as I run through this now. I see things like this, for k is 0 to 9, that's a loop with a fixed number of iterations there. That's the kind of thing that the JIT would be tempted to try and unroll. If your loop was always doing 10 iterations, then potentially you can just flatten that out into 10 iterations worth of instructions and don't have to compile it as a loop. We'll see if there's more of that stuff, but the thing is that there are internal loops here. And those don't necessarily have... This one is also kind of fixed, right? This is looping across a table, and the table we can see has 5 elements. So it might even be that we're getting some nested fixed length loops, and that would give kind of a multiplier effect on how much you would unroll. So it might be that we're starting to see a picture of where you would get loops that the JIT is tempted to unroll but are going to get very long. And yeah, right, and then this is generating... Well, I shouldn't get ahead of myself, right? Because I should be using the profiler to see which lines of code are actually relevant here. So this function actually seems to be creating a data structure that is then used to generate source code. So this is a Lua program that is generating a Lua program that presumably is then loading and running. And that is actually a little bit tricky, right? Because when we see the profiler data, we get the file name is solver, but I don't know if this is a file that exists on disk. This might be in some generated code. And actually in the front end here, we actually have source code. We have the source code in the log, so we could find it here, even if it was generated. We might have to do that. We won't come to that point just quite yet. And the line numbers are quite high, right? We're seeing all of this activity, a few different, but line like 700, 1,000. So is this code that we generate, is it so long like that? What do we have there? Alright, okay, so it's generating a whole bunch of code. We have loops here now, generating things. So I think I would like to see this generated code, actually. I think that would be a useful thing. We don't currently have support for that in the UI for browsing the code in terms of clicking around, but I have made the virtual machine log source code when that is loaded dynamically. We have decoded those events here in the UI. So actually we should have the source code somewhere in here if we go looking for it. So let's go looking. I'm going to hop over here to another tab, which is the events in the log. And it's a little bit slow to select tabs. We did a bit of optimization on this yesterday, but it doesn't seem as snappy as I would like. So this might be something worth also optimizing a little bit again now. One moment, please. I won't do that just yet. Pardon me. Okay, so right now I want to see the source code, and I'm going to scroll down in the log just chronologically until we get to the meteor benchmark, so that we can kind of see it here. Wow, the UI is being really sluggish. That's something that requires some thought and attention. I try to drag the scroll bar. So what I want to find here, I mean, here we see all of the JIT activity from compiling this thousands of lines of generated code. But it would be kind of nice to find the code itself, actually, and fish it out. I don't suppose. Also check if it gets written anywhere. Does it get written to a file already in the benchmark? Looks like it's just getting loaded straight in from a string. It never gets written to a file. It could well be that we are looking for it in the right place here. This is painfully slow. I think we might have to optimize this because you can't have it that's scrolling around in the event list. It takes a really long time. That's not really acceptable. So let's take a moment to optimize that. I mean, I'm clicking here on the scroll bar and I'm waiting like 10 to 20 seconds or something crazy to see something actually happen. So when the UI has caught up a little bit, we're going to find out what's going on there, and we're going to make it run faster because it's not cool. And this is related to some similar optimization like that we did yesterday as well. Hit it with an interrupt. Interrupt that and get out of there. Now let's turn on profiling. As we did before, we're going to turn on profiling in the user interface, profile all processes. And then we're just going to click the scroll bar once. And we're going to wiggle the mouse up here at the top of the screen. And when it's finished processing that scroll bar click, it's going to detect the mouse is at the top of the screen, which is the signal that we want to stop profiling and see the results. And it's going to show us what was taking such a long time. Quite a nice profile, actually, I think, even though I'm not completely comfortable with interpreting the results, but it seems to get the job done quite well. It's an incredibly long time that's taking now, actually, just to scroll in that list. And I guess it's maybe doing on-demand formatting of these events, and it might be that quite expensive to format an event. Let's see. This is the profiler report now. It spent 33 seconds doing a scroll event, and we're going to scroll way down the stack, try and see where the action is. Where is it? Okay, when we want to print these messages, we're trying to show the end source line, and to do that, we're actually decoding all of the bytecodes and then seeing where the last one is. So actually, I guess we're just to show that scrolling list, we're kind of forcing the all bytecodes for the entire log to be kind of fully decoded into objects, and then we're just looking at a few of them to see where some traces ended. So that's probably not the right idea on a couple of different levels, and there's a couple of different things that we could do here. One is we can make sure that the bytecodes are cached, so this is only ever done once. So is that the case? Let's check. At some point, with a bit more experience like this, it will become obvious what the right way to handle kind of caching and everything is on a kind of a universal scale. But it's not yet. Okay, so no, it seems like we do already cache the bytecodes, so it's not that we're repeating work, it's just that things are taking quite a long time. And I think the culprit was this... I mean, just when we're printing these summaries, we don't really want to have to... I don't think that we really want to have to go and force all bytecodes everywhere to be fully decoded. Although should it really take such a long time anyway, that I don't know. Another look. Let's have another look in the profile data and see where all the time disappears. So we're getting the number of bytecodes, and to do that we're decoding all of the bytecodes. And to do that we're creating bytecode objects and decoding them from binary C structs on the heap. We're still 30 seconds unaccounted for there, so the real time spent is coming further down. Now we're getting into time spent. There was 30 seconds unaccounted there. There's only 20 seconds unaccounted there, so what? Then we're getting into this flashback object is the representation of a fragment of the heap at a particular point in time. So now we're getting into the low level kind of actually extracting C structs out of kind of memory fragments, decoding them with dwarf data. So most of our time is spent down there, yeah, actually pulling out. Most of the time is being spent really deep down decoding objects, but the thing is I don't expect that to actually take such a terribly long time, so I'm a little surprised. It doesn't show us here how many times that's being called. I don't immediately see that anyway. Now what if we see statistics here? Can I get any statistics for individual functions, like how often a specific function was called? No, there's a global statistics. What does full report mean? Not giving me anything better. What are the other views? Leaves. Another way to look at the profile of data. They seem better. Oh, I don't really want to expand this all the way again. Can we get that expand all from here? Yes. Get back to where we were for a moment. Where the time is being spent. Is that UI getting a bit sluggish? Better now. Where is the time? Looking, here we go, 30 seconds unaccounted for there. And here, okay, so here's where we were. Well, this might be something. When we decode the bytecodes, we're doing them one at a time, as opposed to in a big array. That might be a mistake. So I guess one option that we have the root thing we're seeing here is that it takes quite a while to decode all of the bytecodes for an event like an attempt to make a compilation. So I guess we've got thousands of compilation attempts. Each one can have tens or hundreds or maybe thousands of bytecodes inside them. And the trouble we have now is that when we just want to list them out, we're actually going deep and decoding every bytecode of every trace just to print some basic information like, you know, how many bytecodes there were, and that kind of thing. I guess the first thing we should do is probably just try to optimize that so that it's fast enough. And if we have any trouble with that, we can maybe be a little bit more judicious about when we decode information. Try and not go too deep too early. But anyway, let's just look at the direct approach to start with. So we're calling this function bytecode values, which is returning pretty raw by the look of it. It's returning int32 values out of the C objects, and that's taking a really long time. Okay, that sounds like a pretty basic and fundamental thing that we can work on. So the context here is that we have an object called rjit flashback. So the high level view here is we have a log file from a just-in-time compiler, and the log file contains raw C structs. And I can pull one of these up as an example. So the internal state of the JIT compiler is these kind of structs like this, and the log file contains just exactly these structs, just written directly to disk as binary images, and then the job of the UI is to interpret those binary images by using dwarf debug information like GDB. So that's exactly what's happening here. We load a file containing a bunch of C structures, we load the dwarf debug information, and we combine them together to try and create higher level representations of things. And what we're seeing here is specifically when we want to get bytecode values, we want to take bytecodes and just decode them into numbers actually. Because each bytecode is represented as a 32-bit number, and we just want to pull these out of the kind of C heap snapshot that we have and put it into just a Smalltalk number, or a dwarf object representing a Smalltalk number, but that's taking a really long time anyway. So we should optimize that. And the immediate thing that jumps out is we have a loop here that then decodes one bytecode at a time. And that may not be the most wildly great way to do things. It might be that we could, you know, decode it as an array or something. If we look at the stack here a little bit, we'll try and see where the time is really getting consumed and see if that can tell us anything interesting. Because the representation we have of the C heap is pretty efficient, but it's not completely free. So the log file contains C objects, and it can log the same object actually many, many times, and then it's really important that when we go looking for a value at an address, like where a bytecode is supposed to be, that we take timing into account. The same memory address might have different values at different times, and then we're going to need to take that into account and make sure that we get the right value. So every time we do a lookup of a new object, it actually needs to kind of go into a reasonably complex data structure that is looking up both the address and the time to get the value at that address at the right time. So anyway, it's actually pretty efficient, but to do it every single time separately for every single bytecode, that might actually be a really bad idea. This might not be particularly well written code. So then what we really want here is to get n bytecodes up to size. We're doing it one at a time. So do we have anything here that can do an array at a time? Although maybe before we answer that question, we'll have just a little bit more of a look at the profiler data. So what we've been saying is that here we have this bytecode values. It's 28 seconds unaccounted for there. So then as we go, and this is a pretty high level function, so it's very interesting that it takes 28 seconds below this on the stack to get stuff done. So then where does time disappear? A little bit goes, quite a bit of time actually goes there, just going from the name of the type, just resolving the name of the type to an actual type. So that would be an easy fix actually, which might be worth doing. But it would be an easy fix, but it's only part of the puzzle. We could just do that job once somehow. And then when we actually decode this type, which will be a 32-bit integer, then we need to pull the bytes out of the C heap at a specific address at a specific time, and then that's what takes most of the time down here by the look of it. So I would say the main problem that we have is this repeatedly going into the C heap, in 4-byte 32-bit chunks. So going into the C heap, it's actually pretty efficient, but it does involve a lookup on a non-trivial data structure to find the right value representing the right time, and we just should do that on bigger blocks. So I think if we just do this in a better way, if we grab an array at a time, then we're going to be happier. So let's see what alternatives we have. So just again, what we want to do, bytecode values, we want to rewrite this to not be a loop anymore, basically. So here we have a loop from 0 to size -1, grabbing 32 bits out of the C heap. And what we want to do is actually just grab a lot more all at the same time. Okay, so let's look at our flashback object to see what other methods like this we have. If I search for flashback, I'm going to resist the urge to digress on the specific data structure that I cooked up for looking into the heap. Maybe I'll explain about that sometime when it's hitting one of its sweet spots, because it's actually quite cool. But anyway, what do we have? Decode. So I think we may want to use this raw function instead. We'll say, I think that's quite a reasonable thing to do. We'll just pull the bytes and then we'll decode them kind of manually, right? So we're going to say, what was that function again? Pardon me, hop back into the flashback for a moment. Bytes at with a size. Okay, bytes at an address with a size. So instead of this big loop, we're going to say data is PC proto flashback bytes at, and then we need an address. Something like that. So if we say that, we declare a local variable called data, then we've got everything out of the C heap, and now it's only a question of doing the conversion into numbers, and that should actually be pretty straightforward. So if that's a byte array, let's see how we're doing that already now, actually. How does the dwarf object decode itself? Dwarf base type will be the one. That's going to be something we decode out of the C heap. How do we... Here we are. So in a Smalltalk byte array, there are actually a whole bunch of efficient built-ins for accessing basically C data types. And when we decode dwarf information, we just pick a suitable method. But in our case, we know that we want to get an unsigned long, 32-bit, and I believe that index is from 1, if I'm not mistaken. So anyway, we've got this data which is going to be a byte array, and we want to turn that into a collection of 32-bit numbers. So we'll do a loop here, but instead of on each iteration going into the C heap, we'll go into this local array, and it should be a lot faster, I would imagine. So if we say, so we keep that line exactly as it was, and just when we collect things, we're instead going to collect data unsigned long at we'll want to do it like this, I think. The array will be 1 based. No, that's not really going to work, is it? 0. That might conceivably be something, actually. Oops. So what we have there on that code is just we want to decode some bytecodes, and we do like a big wholesale decoding, or just fetching raw of a fragment of the C heap at the relevant time, which is implied in this object here. Long story. And then we just pull all of our values out of that chunk. So it's only one trip into the C heap. Let's save that code and see if it makes any difference. I might turn on profiling right now. So that's what we're going to do. We're going to turn on profiling, then we're going to click on the scroll bar, and we're going to see if it takes a long time, and if so, why. Start profiling, yes, and click on the scroll bar. It's still taking a long time. Okay. Let's have a look at the profile report again then. Okay, much less time, but still significant. So before we were taking like 30 seconds, and now we're taking something like 6 seconds, which is still way too long. Let's see what the problem is now. This is still the same function taking a bunch of time. Why does it take so long now? Okay, so it's still the same operation taking a while. It's just now we're only fetching raw bytes, but that still takes long enough. I guess the issue is just that there are quite a lot of these bytecode. I'm a little surprised that it can take so long, but so is this reasonable? Should it take? We only did a screen full. Let's try and make this into something a little bit smaller. Actually, let's find one of these. Do this on one kind of function at a time. So here we have a trace. Give it raw. Let us pick one of these events. And can we get the byte codes? Okay, so there's just calling it manually. And it was bytecode values, right? Where was that? The prototype object. Also is potentially significant. Are we regenerating these prototype objects all the time? hadn't thought about. Prototype is a representation of a bytecode function. This is immutable in the heap, so we only need to decode it once, but it's possible that we're decoding it a bunch of times. Let's check if that makes sense. Here we have the JIT state object, and we decode that. Okay. So every time we want to touch the prototype, we are doing a new decoding of that. So again, I don't have a kind of grand unified vision for how to do the caching in the user interface yet, in a good way. But I feel like I'm doing it incrementally, and each time we get a little bit better of an idea, a little bit closer to but hang on, that's going to be the starting prototype, but each bytecode could also refer to a different prototype. Come to think of it. So when we're looking at the bytecode reporting log, to see how many places there are that we're creating these prototype objects, and what would be a good way, oops, that was the wrong, what would be a good way to avoid duplicated work. Here is where we decode a bytecode. Are we doing anything wildly inefficient here? Well, maybe. We're creating the prototype object there. So maybe we're doing that a hilarious number of times. Maybe we're very, very, very often creating these bytecode prototype objects. Is now the time? Probably not quite the time. It must be getting very close to the time that we should have a unified way to do caching of high-level representations of low-level objects in the C heap. So basically, when we look up an object of a particular type at a particular address at a particular logical time in the C heap, that's something immutable that could always be the same. I would like to special case a little bit more, just to get enough experience to be sure that we don't invent something far too complicated. So where are we? Budget bytecode, where do we create those? And we get references to this class. There we go. What I want is that every time we go out to fetch there are different levels where we can do the caching. I think what what is appropriate. It's an unusual data structure that we have, where we have something representing the C heap, and we index into it with a type, an address, and a time. And the time can change a lot, but very often nothing will have changed in an object from one time to another. So it would be nice to take that into account in some reasonable way. So, you know, be able to get the same cache hit even if you check at different times, just when that object hasn't been changed. And I guess the way to do that would be by requires some pondering. Let's pull up our, I don't have the profile data there right now. Let's go back to the profile data for a moment. Get a new one. We're getting to the point where time is getting burnt. There we have like 14 seconds unaccounted for at that point while we're printing events. And then we want to get the end source line for the printout. To get that, we want to get the number of bytecodes. To get that, we want to decode all of the bytecodes. And then we're decoding individual bytecode objects. That's calling into okay, but the expense there is actually still this okay, the expense is still this pulling the bytecode values, and we already optimized that function, but maybe now we're just calling it far too often. We're calling that again and again, because we keep, that could kind of explain things. It looked like in the code that we were recreating these prototype objects very often. And if each time we create the prototype object, it also kind of implies that we're going to refetch the bytecodes, then it would make sense that we're spending an awful lot of time fetching bytecodes out of the C heap. And then even after we've optimized that, I'm still calling it so often that it's a problem. So I do think that when we decode bytecodes, we don't want to be recreating the prototype every time, because this line of code, I think, is the problem. Each time we want to decode a bytecode, we decode the object representing the bytecode function, and via that we end up fetching out a whole bunch of stuff. I'm not completely convinced of that explanation there. Does that agree with the profiler, which says that we briefly collapse that? Okay, we're spending a lot of time here, we see specifically in decoding prototype objects and then getting them to do their bytecode values. So yes, I do think that this line of code is specifically the problem. We don't want to be we want to be just reusing that, and maybe in just a simple way. So let's just put a little bit of cached interface onto that. Again, not getting too fancy just yet. We have this object, and we're creating that. We're saying new, and then we're saying from, and giving it a GC proto object. dwarf object. And I think we'd just make a class method called from takes a GC Proto object like that, and we're just gonna cache this. So the cache miss case is going to be we have a cache miss case will be to create a new object and initialize it from the dwarf data, and we're going to return the proto. But we're going to have a dictionary somewhere. We're going to say we're going to have a cache dictionary, and instead of just returning that object, we're going to return cache at, we're going to get a calculator key for the cache. Maybe to begin with, the key will just be this object by identity, and if that doesn't work, we'll think about whether we can construct something more appropriate. Okay, the cache at GC Proto, if absent put, but if there is a value in the cache, then return that. Otherwise, we're going to calculate a value and put that in the cache and return it. And that value is going to be this thing that we had down here. Don't need the proto variable now. Any local variables, actually. So let's try that. Let's try that. Now here, if instead of that, we would comment that out like this. If we say prototype we ask the class to give us a cached instance of the same thing. Then let's see what happens. Let's see if everything blows up and goes to hell, or what happens. Click our scroller there. And I guess we maybe don't expect this, or do we expect this to have a good effect already in the beginning? I'm not sure, because it's meant to cache things for the next time. We're running dog slow, so it hasn't, but now it's getting a bit better. It doesn't seem to be having a really wild effect, and I suspect that maybe we need to construct a cache key a little bit differently. So let's do that. Instead of caching by the identity of the GC Proto object, let us instead extract some meaningful information out of that, like its address, its value, time. Flashback, yeah, give us the timestamp. Well, time. Okay, so let's suppose we construct a key. We construct a key, which will be an association of, there's an array of an address and a time. The address is going to be, I think it was the value. I could be wrong about that, but we'll put a breakpoint in to check that. And all the time, let's see if this works any better or blows up. When we click back to places we've already been, it works really well. So you kind of get the feeling that it's working well for caching old stuff. So I was kind of imagining, it doesn't really seem very effective, I gotta say. Let's look in our cache and see what we have. What's it getting populated with? That was in the object budget prototype class. There is our cache. It has 50,000 objects in it. Which is a lot. 50, yeah, that's too many. We shouldn't have 50,000. We don't have 50,000 bytecode functions. I mean, we're dealing with generated code here, so there might be a lot, but that seems way excessive. Okay, so I don't think the cache is working properly, so let's have a look at that. What do we get here? Keys. Okay, that I pulled an inappropriate value. That's a straightforward bug. Try that instead. And experiment a little bit there. I need to think a bit about what. Let's clear the cache while we're here, so we can see just new values. We will say that cache is nil. Click around a little bit again. Taking about 6 seconds still, so we haven't fixed anything. And what does it say? What does the cache look like now? $50,000 entries still. That's okay. So that's wrong. What do our keys look like? We still have the same. It didn't clear. Sorry, I meant to clear that, but it apparently didn't clear. Let's try again. Now the cache is not there. And this live coding sure is exciting, eh? I guess a lot of programming is just patiently following a train of thought to its logical conclusion. That is fine once you're there. And now I want to look here again. I want to see what the cache looks like now. 231 objects. That sounds much more plausible to me. These look like addresses and timestamps. Seems pretty reasonable. Okay, but it still took a while. It would be interesting to profile it again, actually. So what did we get last time? Last time we spent... Yeah, clicked twice on the scroll bar and it took about 14 seconds, so like 6-7 seconds per click. Let's see if that's the same. Let's see if our situation has changed in any observable way. Profile. Okay, here's our new profile. How nasty does it look now? Okay, so it's actually quite a lot better. I think it was 6 or 7 seconds per event, and now it's more like 2.5 seconds. So it's not good enough, but it's better. So what's the problem now? Is it the same problem? Getting the end, still getting the end source line, getting the number of bytecodes. Still decoding the bytecodes. It's taking a long time. What are the bits of bytecode going to take a long time? It's mostly getting the bytecode value. Some low-hanging fruit we could probably get rid of, but not the hotspot. Let's follow the profiler. Okay, that's just fetching the bytes. So it's a function that we already optimized. The question again is it too slow, or are we calling it too often? It would be really nice if the profiler could tell me that. I guess if it's a sampling profiler, it won't know, but I would really like to know how many times that function was called. So that this function caches. Does it do that correctly? Looks like it. There's a variable called bytecodes. When you ask for the bytecodes, if this is okay, yes and no. It caches for one event. We've got a lot of events. So this code is still going to be called quite a lot, because each event will need to be decoded separately. And when we scroll, there'll always be new events. Okay, so yeah, we're spending a lot of time in here. And mostly down to the bytecode values. So most of that time is still getting burned down in here, which is the function that we already optimized. Don't know if it's reasonable. Optimize that a lot more right now. A bit of time on that in the past. This basic collection machinery might actually be something we could optimize. That's half a second spent there, so that's about 20% of our time. So are we at the point where we're worried about stuff that takes about 20% of our time? So we might have even seen something a bit more obvious a little earlier. I did actually see a little bit of low-hanging fruit that I'm just going to grab right now. We had this function to go to bytecode. Where was that? We need to decode based on a type, on a C type, and we search the dwarf debug information for the enumeration that includes BC loop, and that is taking some time, not a huge amount of time, but that's taking some time. Here, 250 milliseconds. Okay, so that's about 10% of our time. Is that something that could be remembered somewhere? Although, hang on. Let's see why that takes time anyway. Down the stack we go. I mean, if this is just doing string comparisons, maybe I should change that string into a symbol. So it might be that we're doing string comparisons when we can do symbol identity comparisons. I'm going to just try that, because that's something that would potentially have an impact everywhere. Small thing. I'm just reacting. Where do we find that function again? Here, I gave the name of ctype as a string, but I could have given that as a symbol, which I think then means it can be compared by identity instead. And let's just say, make sure that it's symbols all the way around. We have the dwarf enumeration type. Make sure that's a symbol, perhaps. Okay, now I'm going to actually just go over and reload the whole thing. This is just a tiny little thing, but I think that could potentially be useful many times. One thing is when I'm not writing Smalltalk code all day every day, so when I wrote this code originally, I think I used strings for a lot of things that should have been symbols, so that when you're doing lookups, it's just more efficient if you use intern strings rather than generic strings. It seems worth going through and making it so. And that's going to run, and I guess it's going to format this. It's going to take a little while. You know, it's actually a big topic, the whole business of when do we compute things, when do we cache things, how do we cache things, because we're just doing this in the context of the user interface now, so we want to have fairly low latency. Like now we're waiting for it to do something, and this is a bit annoying. So generally we want to avoid cases where the user, us, is waiting for a response. We've taken some action, we haven't got the response yet, and one way to do that is to do work incrementally, so don't do too much upfront, but rather give it some time to, don't do everything up front, but just do the minimum that you need at any given time, and then do everything kind of incrementally and on demand. And the risk with that then is that if you don't cache in a disciplined way, you might end up repeating work again and again and again when you need to use things. And that's kind of the dilemma that we have now, where we do things a bit incrementally, and sometimes we do them too often, and we're trying to figure out the best way to cache and remember that. Another thing just to know is that we have nicks under the hood. So here we are in a single-threaded, Smalltalk image, but we actually have a beefy machine, lots of CPU and everything. So we can do background processing, and Nix has a very sensible approach to caching. So a kind of a bigger topic is whether we can farm out a lot of this work and kind of have a lot of things pre-processed in the back end, so that it's already ready when the UI wants it. Meanwhile, how can that be taking so long? Everything's running super slowly today. I wonder if that's because I broke something. I guess there's something also to think about. Probably the worst case in the tooling is always going to be when there's a lot of generated code, like what we have here. where you have a program that's generating source code that can be extremely long and just kind of very different to handwritten code. So it's actually a really nice test case to have thousands of lines of generated code that we need to deal with. Thousands of lines is not very much, so it shouldn't be a challenge, but just haven't exercised that before. I'm getting a little impatient, so I'm hitting that with an interrupt to try and understand what it's doing. Waiting. Why would it be waiting? Try again here. So if I run again. I'm hoping to just rerun the whole thing. I don't know why that would be a problem. Look and see if the backend is busy. No, there's no Nix process. Got a gazillion Pharo processes because I've been leaving all of the old ones running. There's a lot of CPU cores, so it doesn't matter. It seems to have got stuck waiting on a subprocess. We've seen this happen before a long time ago. The bug that we know about there we already fixed. Just check if it could possibly be that same issue. There was something, a deadlock with process output. Just follow this wherever it might lead. What we want is to make sure that the standard error is always being redirected to standard out. That's not happening there. Hold on, so how do we miss that? Nix instantiate, maybe we miss it on. That's interesting. That's important. I don't understand why we don't have that code. Something that bears thinking about. Put it in where it's supposed to be, which I think is here. It's supposed to there say now what about if we run again? Is that going to work? That was a deadlock bug in the library for doing operating system processes. If they print a lot of output to standard out, then the UI doesn't read that, and they end up blocking on there. On standard error. UI doesn't read that, and they block there because the UI is trying to read from standard out. The process is trying to write to standard error, and it gets locked because you actually need to read from both at the same time. We had worked around that by redirecting standard error to standard out. Why isn't that doing what we want here and now? Oops. Is that really running? 4005? Nope. That process has terminated, but we haven't detected that it's terminated. Okay, so now there seems to be some whole new bug. Can't be related. Why are we waiting? Why have we not detected that that process has terminated? We're polling at a 50 millisecond interval. We're polling this is complete. That's returning false, but why would that return false when known as defunct? Okay, but hang on. How is it how is it expecting to discover when this process is complete? I immediately see that. I don't like having deadlocks in the subprocess library. I'm kind of tempted to just find something a bit more direct that we could use instead. Why do you consider that to be running? I guess when call up to end, that is supposed to somehow read the output and I guess mark we're finished up to end. I don't immediately see. It must be there somewhere. How do we detect when it's finished? What makes this polling loop actually work? Output on. I think the process is just complete. This is an annoying bug. I didn't really want to be spending time on this, but here we are. I wonder if there's any other simpler library for dealing with subprocesses, because this one is kind of surplus to requirements, and it's not the first time we've had to chase stuff around in it. Follows through a bit. This is trying to read all of the output from a process and then return. So it's looping until the process is complete, which sounds fine. And it's waiting 50 milliseconds, which also sounds fine. And then it's taking all output up to the end of output currently available from the process and putting it onto a stream. And it goes back here to looping on is complete. So somehow that is complete flag should have changed, but didn't. Let's see if we can look at the process a little bit more again. What do we got? have our Pharo, we have 3 Nix instantiate processes. That's why I've got all of that. What is that process? Okay, so this is a problem we have with a few defunct processes. Which I think just means we haven't noticed they've terminated, but we haven't noticed that they've terminated. So let's have a look again at this up to end. Seems a little boring. Let's debug that. Let's step into that. Out of that. Timer 4. We're going to get into let's really see what is this mutually excluded block. What's it going to do? Super up to whatever. A breakpoint there. Try this again. So what is pipe from output? Next pipe object. Hop into that. Call. Is the reader closed? False. What is the reader? Profit async file reader. That's a little suspicious. Is it really not closed? Why would that be open? No. Very suspicious. Doesn't think it's at the end. It's in there. I want to get a better look at this object. I don't think this is right. I think that this represents something that is closed and dead. Oh, are we doing signal-driven AIO stuff? Did something just get mixed up? Oh man. I'm not really comfortable with that actually. I don't want to deal with that kind of asynchronous I/O stuff. I just want to make sure that we always detect for real. If it's doing everything kind of event-driven, I'm maybe jumping to conclusions here, but I don't want to go through a lot of kind of I/O event-driven stuff. You know, I just want to know if the thing is dead or not. Is there any real object here? File ID, might be a file descriptor or something. Much too big of a number. event handler, dare I ask? So did we just miss an event? Can we call this changed method? What about if we just say self-changed? I'm guessing, of course. And we proceed. Nope, we still end up in this polling loop. Now I just want to kick this process and make it realize that it's finished. Update run state sounds promising, right? We ask this object very nicely. To update its running states. Seems to get blocked somehow. Hit it with an interrupt and see where. Are we maybe already inside? No? Maybe, yeah, okay, maybe we're already inside a mutex or something. In that case, it's not really going to get away with that. Okay. Whatever. Let's proceed from there. We've got an error at least. I don't really think that we're out of the woods here. Let's try applying that trick a little bit. Run that. We're expecting it to hang again because that's what was happening before, which is annoying, but it's something we can debug. Hit it with an interrupt. Now, where do we have a process? Delay object. There's a process object. We can tell this. Was it that object we could do it on? It still thinks it's running. Okay. This run state change thing didn't work. Where the heck do we have a changed method? Then a changed method. Where does it get it from? Was it external? Yes. Where are we? We're in a Pipeable OS process. What does that look like? Ah, maybe that's the object that needed to get pulled. Now it sees that it's terminated. So if we proceed, we get an error. Okay, that actually seems kind of promising. I'm not very happy about it, but I think we can deal with this. So here we go. We try to run a build. It's going to get stuck. It's going to annoy us. We're going to press interrupt. We're going to go into this loop of ours, and we're going to put in some explicit polling here. We're not going to rely on this to happen just kind of independently. We're going to say process proxy, something like that, shall we? Oops, process proxy. Attribute name. That wasn't changed, it was updated before. Okay, fine. Why can't we see process proxy? It's because we're in a parent class there. For the love of God. Is complete. Maybe we'll change is complete to do that, you know? When we say is complete, I want to actually get that information from the operating system. Process proxy, okay. Looking for an external OS process, which maybe is an object that we should actually be using directly. This is something that we could come back to and see if we're going really roundabout. I don't know. Anyway, one bastard thing at a time. Run state. Okay. When we do this, what we want to do is complete. The code that we just wrote. Okay, it was not in code change in debugger. We asked an external Unix OS process to update its run state. When we have an external OS process, it's the Unix version, and it is complete there. And it is complete here. Self run state. I don't think I want to be caching that run state. I think I want to just fetch it every time because I'm paranoid. So is it asking for trouble to say this? Am I going to cause some horrendous infinite loop? Let's see. Quite possible. Something is stuck. Let's hit it with an interrupt. Yes, doesn't seem very happy at all. Okay. Managed to crash the process. I think I'm going to break for lunch and then come back and have another go at this. This was some days you win, some days you lose, and so far it's mostly losing today, it seems. So that's life, hey? I'm going to come back. I'm going to update Pharo code so that when it runs a subprocess, it always, when it's checking for completion, it always gets that information fresh from the operating system, and do that in a good way. And the other thing that I'm going to do then is finish optimizing the code so that clicking around is nice and snappy. Back to that in a bit. Finished now.